All right, so I'll just do one video here on multiple choice, then I'll do two separate videos, one for each of the two short answers. So here we go. The big thing about this topic is just realising that there are, angular quantity equivalents to every linear quantity equation we've studied in this course. All right. So what I mean by that is, here is our linear version. I meant to do that. Our linear version of e squared equals u squared plus 2s. So that's the same as saying the final angular velocity squared must equal the initial angular velocity squared plus, rubbed out my 2 accidentally there, 2 alpha delta theta, because change in theta is the same as change in displacement. Do the maths on that, and it comes out to be a beautiful 10 on pi. Why? Because the displacement is 10 revolutions. 10 revolutions means 10 lots of 2 pi, which is 20 pi. This one here, this is the linear version of force times time is change in momentum. What we're saying here is that angular torque times time is change in angular momentum. So 6 times time is 12 times 10, 20. A lot of you got the first two questions wrong. They were quite simple. This one here is a little bit trickier, right? This one on the right has the much higher moment of inertia. Now, up until this course, we would have told you that the initial kinetic energy becomes, the initial potential energy at the top becomes pure kinetic energy at the bottom. What we now know, though, is because something's rotating, some of that energy is converted to angular kinetic energy. Now, as you can see, that depends on the I, the moment of inertia, yeah? And if omega is simply V on R, which it is because V is omega R, both of those terms now have just got a V squared in there. So what I'm really saying here is if you've got a bigger moment of inertia, you're going to have a larger proportion of the initial potential energy becoming kinetic, yeah? Angular kinetic, meaning that there will be less linear kinetic energy, all right? So that means the disk, our friend the disk over here, right? The disk, which has got a relatively small angular momentum because its mass is centered at the axis, or closer to the axis than the ring, is going to have a greater linear velocity and therefore will get there first. That's how I thought about it. This one here, really you just had to get the numbers right, and I think a lot of you missed the point that the centre of mass of the beam was 0.5 of a metre from the pivot, okay? Some of the clockwise and some of the anti-clockwise, okay? So what do we know? The 20 kilogram kid whose weight will be 20 g times that distance, yeah? It's going plus this is the torque caused by the weight of the beam. That's going to equal the torque caused by the heavier kid, and it comes out to be 0.68 of a metre. Very easy question, so many got it wrong. And I think you're just not analysing the dimensions, the data on it. Simple question. This one here, another very simple question. Right. I always draw diagrams. I'm not very good without drawing diagrams. So there's three forces acting on it. The reaction force at P, the weight of the boom itself, and the tension. Now, the clockwise torque is caused by the mass of the beam. It's acting at the midway point. And then the tension is causing anti-clockwise torque. It's always the force times the distance times the sine of the angle between it, because the sine of the angle gives us the perpendicular component of the force. Happy times. So that should be 65 kilos. Not a hard question. Here, what caught you by surprise was this. A lot of you said the change in angular velocity was 10 because 25 take 15 is 10. But don't forget to change direction. Remember from linear days, if something hits the wall at 15 metres per second and bounces back at 25 metres per second in the opposite direction, its change is 40 metres per second away from the wall. Same here, angular velocity is a vector. It was going anti-clockwise. The change is in the clockwise direction. If the change was only 10 in the clockwise direction, it would have still been doing 5 in the anti-clockwise direction. You with me? So then it is simple in terms of 0.5 times 40. All right? Makes sense? because the moment of inertia was that, and the change in angular momentum is certainly is just simply the moment of inertia times the change in angular velocity. Next one, a constant torque acts on a bicycle wheel, rest, final, radio. So look, this is the linear version of S is u t plus alpha a t squared. This is the angular version. Delta theta is initial omega t plus half alpha t squared. Plug the numbers in, we get 32. All right? I don't think that's that hard. It is hard because you're trying to make this transition from the linear to the angular world, but physics is a doing subject. The more practice you do, the better. Just like, question 8, just like the area under a forced time graph gives us impulse, the area under a torque time graph will give us angular impulse. So it is the area under PQR. That was actually pretty well done. Next job. Here we go. A little bit of working out here. Hardest question by no small margin, I reckon. So the initial angular momentum was the moment of inertia of the disk on its own, which is half mr squared, and times that by omega. That'll be the same as the final angular momentum. Now remember, with moments of inertia, we can just add them. Now the moment of inertia of this little body that was dropped on it, there was a question in SOCOS like this, where it was a drop of mashed potato or plasticine or something landing on it. So that is what I'm just highlighting now in green is the moment of inertia, the extra moment of inertia. I've made it small m. All right. Now I'm just rearranging it to get omega f by itself. As you can see, I've divided by little m r squared plus half m, big M r squared. The r squareds all cancel, which is very convenient. Then what I did is I divided every term by half. So the top just gets rid of the half. This bit here gets rid of the half. Dividing mr squared by half gets a 2, and that gives me a very hard question. Okay, no one really gets 100%. People who do get those questions right. Okay, this one here. I made this one up from scratch. I hope you're pleased with my efforts. So what I wanted to do here is work out what force is applied. And I guess, right, torque times time is the change in angular momentum, which is I, change in omega. I'm just going to write under here. That's the same as saying force times time is change in momentum, which is m delta v, yeah? But this is this here is the angular version of it. All right. So I want to know the force. That's my only unknown. It's acting at a 0.2 distance from the centre. So that's the torque caused by it. That's the time. Yeah. And this is I outside of change in angular velocity. And it comes out to be 4. Not a terribly well done question. Here we go. This one's, guys, please. This is an angular velocity time graph. The slope of a normal velocity time graph is acceleration. The slope of an angular velocity time graph is therefore angular acceleration. Simples. Now, the area under velocity time graph is displacement. So the area under an omega time graph is angular displacement. So the angle rotated, not number of revolutions. I think you'd have to, divide that by 2 pi, something funky. The total angle is measured in radians, my friends, not revolutions. Here we go. Now here's a philosophical question. If there is no torque, is there torque? It's a philosophical question. The IB says the answer is C. Zero torque is the case where there is the least torque, because zero torque is smaller than any torque. Well, I could argue both sides, guys, but I guess if you've got 0 voltage across a resistor, does that mean, there's no voltage? No, there is 0 voltage. I don't know. This is the answer they gave. If it was worth 2 marks, I'd give you 1 for choosing D. Next one. Disc rotates with an angular speed of 10 and has an angular acceleration of 2. By what angle is the disc rotated? Now, this is the angular equivalent of v squared equals u squared plus 2as. There it is. Plug the numbers in. Final is 30, initial is 10. What we're trying to find is delta theta, and we get 200 radians. Happy times. Next one. a symbol of mass m, radius r, blah, blah, blah. The moment of inertia is half mr squared. That's going to be important. See how I highlight the important numbers and important facts. The kinetic rotational energy of a cylinder is K. Another cylinder has mass 2m and radius 2r. Okay, now I guess what I wanted to do here is let's just get that equation out. So the new equation will be the new kinetic energy is K times the old kinetic energy, which has been scaled up. Now, can you see that? What's happened here? We're saying the mass has gone up by 2, so it's going to double because of the mass, right? R has doubled. Now that means that, what does that mean? That means that it's going to go up fourfold because the radius is increasing. And with angular speed to omega, now it was omega before, so if you're doubling the angular velocity, there's another square happening there, so it's going up 4 times due to the angular velocity increasing, 4 times due to the radius increasing, and doubling due to the mass. It's a total of 32. Wasn't terribly badly done. I'm going to leave that. I'm going to make a new video on this in case I make a mistake and have to re-record the whole thing. So I'll see you on the other side.